Hello. In this video, I will show you how to create basic parameters and logic to control CNC channel. It is a continuation of previous videos where I was showing how to create and edit initial parameters, PLC, and HMI. All those videos are located in the same location at YouTube under Electric Drives and Controls, Product, Support. So we'll use latest version of IndraWorks Engineering software and open our project from previous videos called MTX Initial PLC. We'll keep this project untouched and then create and work with a copy MTX Initial PLC channel 1. First, we switch our control online and configure system parameters. So in main basic NC configuration, we can set a number of channels in entire machine. Please note that for every parameter, we can show additional information by clicking on Information tab. That opens for us a help page with detailed description of this parameter. Every channel is an independent part of the machine, capable of running and interpolating up to 8 axes. Typically, it is configured as milling or turning station with its own memory allocation, coordinates, NC programs, subroutines, offset, and so on. So depending on hardware platform, we can have different maximum number of channels. For XM42 MTX standard, we can have only 2 channels. For XM42 MTX performance, we can have up to 12 channels. And for XM42 MTX advanced, we can have up to 60 channels. For L platform controls and version 14 firmware, it is very similar. So for L45, we can have 2 channels. For L65, L75, we can have up to 12 channels. For L85, we can have up to 60 channels. And for MTX Micro, we can have maximum 2 channels. We will leave our main configuration with 1 channel and move to basic parameters. Here we can configure additional, much more detailed parameters for our channel. You will see that there is a lot of parameters and most of them are dedicated and used only with special functions. So we'll focus only on parameters that are always used on typical machine. We'll start with channel initialization. And first we'll look into parameter channel status after channel restart. When we click on this parameter, a special window shows up with a list of NC commands. To verify what those commands means, we can look into MTX NC Programming Manual. So command G62 means deactivation of exact stop function. Command G48 means deactivation of tool length correction. And for example, command BCR means deactivation of workpiece position correction for placements. So you can see here that all those commands deactivate all special functions used in the program and put our channel in default status, ready to run again. If we need more steps during initialization, or we need different steps depending on the machine status, we can use special program called initialization program. There is a template of this program located in NC file system. then FEPROM, and called channel 01 ini.prg. This file is located in FEPROM directory together with our templates, so it cannot be edited here, only viewed. So we look inside and we can see that this program checks internal register SD30, and depending of this register, we'll run different initialization sequences. There are 4 local subroutines prepared in this program. First is prog and prog, and here we have a default command recommended to run after program end of main program. Second is local subroutine with name channel reset program. Here we have commands recommended after channel resetting. Next subroutine is for system resetting. And the last one is for normal NC program. Now we go back to beginning of our program. And here, depending of conditions, we call one or more of those subroutines. So for example, for channel reset, we call subroutine prog and prog, and subroutine channel reset prog. For system reset, we call 3 subroutines: prog and prog, channel reset prog, and system reset prog. As I mentioned before, this file is a template and we cannot edit it here. So to modify this file, we leave a template untouched and copy it into directory where we can edit files, for example, mount directory. So now, if we want to change, for example, initial setting from metric to imperial, we can open the file and modify prog and prog subroutine. If we need additional program to be called after system resetting, we can add it in sysresetprog subroutine, and so on. For this modified file to take effect, we must copy it into directory user fap. You can find more detailed information how to handle initialization files in our YouTube video CNC MTX file system. Going back to our channel parameters, next very important parameter is automatic program reselection. When we want to run NC program in a channel, first we need to select a program from program list. Then after finishing, program is automatically deselected, and in order to run it again, we need to select it again. If we want to keep program selected, we need to enable automatic program reselection function. Next important channel parameter is maximum path velocity. This parameter sets the maximum feed rate that can be programmed in this channel. It is set by default to a huge value of 1 million millimeters per minute, and it should reflect actual capabilities of our machine, so we'll set it to 1000 millimeters per minute. Next important parameter is feed rate override. Here first we set the maximum of the override. It is by default set to 120%, and it is typical for most of the machines, so we'll leave it that way. Next are the steps for this override. It is a table of up to 32 elements, and every element contains a value of feed rate override. For example, in default configuration, table element 14 contains value 80%, and table element 16 contains value 120%. There is a special register in MTX's PLC where we write to it our table number to set the override. So to set override to 60%, we write their value 12. This type of override controlling works the best with multi-position selector switch. So every position of this switch will have its number and corresponding override value. If we do not want to use a table and want to directly write an override value to the register, all we need to do is set all values to 0. Next important parameter is maximum path acceleration. It configures maximum programmed acceleration of our tooltip. It was initially set to 10 meters per second square, and for now we'll leave it that way. Next is maximum path deceleration, and we'll leave it with the initial value, same as acceleration. Next, extremely important part of channel configuration is setup of axis coordinate system. It is so important that I made a special video dedicated to this configuration for multi-channel systems. This video is located on YouTube under a name CNC MTX XM42 machine coordinates. We are setting up a simple one-channel system, so we can leave default configuration. And our axis will have channel name the same as system name. So first axis name is X, and axis classification is main axis X. Second axis name is Y, and axis classification is main axis Y. And third axis name is Z, and axis classification is main axis Z. All those parameters are modified, but not activated. In order to activate them, we must restart our control. After download, our parameters are activated, and now we can focus on PLC logic dedicated to control channel 1. So first, we'll add a new program, name it PR channel, and select ladder logic diagram as implementation language. New program shows up on our list, and after we click on it, editor opens up. But before we can write a logic for our channel, we must prepare a connection interface with signals from PLC to NC kernel and back from NC to PLC. What are those signals? We can look into built-in help file, then system MTX, then MTX PLC interface, and here we can see channel-related interface signals. In the general overview, we can see that MTX PLC provides a dedicated structures with all signals necessary to control a channel. So for channel-related outputs, we can see here signals and addresses for selection of channel operation mode, activation of channel reset function, or NC start command. The same is for all input signals from NC side to our PLC. If you need a detailed information about those signals, you can find those in a signal description chapter of our help file. For example, here is a description of channel reset function. You can also find description of those signals in PLC interface manual in chapter 7. In our logic editor, when we go to Library Manager, we can see that there is an automatically implemented library, MT-base. It is a system library, and it contains all basic constants, data types, global variable lists, function blocks, and functions. So we can go to Data Types, then NC PLC Interface, and here we can see ready structure, MT_ICH_type. When we click on it, we can see inside, and here are all input signals from NC side. There's also structure MT_QCH_type, and it contains all output signals from PLC to NC. Next step, we'll go to MTX NC PLC Interface Editor, and here we can add a channel interface to our project. We can see that first channel 0 interface was added. We can recall from our help file that interface for channel 0 must be added to our project and is internally used for switching functions. Next, we'll add interface for channel 1, and this is our machining station. When we click on this interface and then go to Channel Interface IEC Objects, we can see that system created for us two variables. First is Channel Interface 01 in type MTICH type for all inputs from channel 1. And second is channel 1 interface 01 out type MTQCH type for all outputs to channel 1. Those variables are right away ready for us to use in a PLC logic. So to command NC reset for channel 1, first we insert new coil, then we just start typing a name of our new channel 1 interface variable, and built-in smart coding function will give us a list of all available variables. We pick channel interface 01 out, then we type dot, a list of signals shows up. We can scroll down and select signal QCH_CTRL reset. And here you can see how our command will present itself in a rung of logic. Before we go to next step of our logic, let's look into our help again. Please note that in many instances, information sent to or coming from NC is represented in more than one bit. For example, operation mode is represented by 4 bits. Channel state is represented by 5 bits. We can look into detailed description and make a special logic to decode this information, but there is an easier way. We'll go to Library Manager and add new library, MT_base additional. When we look inside of this library, under Program Organization Unit, POU, then under Channel, there is a function mt underscore ch get state. We can click on it and description shows up. We can see inputs and outputs of our function, and they match states from help file description. We can see graphical representation of this function and documentation. Back in the logic, we'll add new network, and here insert empty box. Next, we'll assign our function to this box. So first we click on name. Input assistant window shows up. Since it is a function, not a function block, we select module call. Then our newly added library. And then we select our function mt underscore ch get state. Our function shows up in the logic with all its inputs and outputs. There is one input to this block, and we'll assign into it our entire variable channel interface 01n. For outputs, right now we use only 3 of them. So first we use output error and assign to it variable ch1 underscore error. System automatically opens for us auto-declare window. We'll declare it here as local variable without any initialization, and we let system assign next available address for it. Our new variable shows up automatically in declaration list. Then we do the same with output ready assigned to variable ch1 ready, and again with output prog running and variable ch1 prog running. We can check if our logic with box is okay, but in order to do it, we must first assign our program to a task. So we go to task configuration, then PLC task, and then we add call and select our program PR channel. Now we can build our program, and right away system gives us a list of errors. We can click on first of them, and system points us to the place in the logic where error happened. We can see that our problem are those unused outputs with 3 question marks. To solve it, we can right-click on our block and use built-in function remove unused function block call parameters. Now we can compile again and see program ready with no errors and no warnings. Next, we'll add a new network and set a coil. This coil will be an error light on our HMI, so we name it LT error. Auto-declare window shows up. And since this video and the project is a continuation of previous presentation, we have already a global variable list, GVL HMI, where we keep all HMI variables. So for auto-declare, we select scope variable global, and object GVL HMI. This list opens up automatically, and we can see our new variable declared at the end. I'll move this variable to keep it together with other lights and add new push button PB reset. Back in the logic, first we add our channel state error signal to control our error light, and to alert operator, we'll make it blinking. To control channel interface control reset signal, we use push button PB reset. Next, we'll compile and download to test it. Back online, and we can see program running. We'll test it using already configured VDP15 HMI. There is also a built-in function when we can see our logic variables available for HMI. So we click on View, then Other Windows, and then Process Variables. New window shows up, and here we can see all active variables available in the PLC for use in HMI. So we start our operation panel simulation. It will take a couple seconds for our panel to show up, and then we'll focus on operation push buttons. So first we'll activate editor by holding this tab for a couple seconds. Then we create a new panel and name it VAM test. This panel will have 3 buttons per line with 7 lines. Now we added first button, and it is for mode selection, automatic. First, we'll select a PLC variable that will activate LED in the push button. Please note that system automatically gives us a list of process variables, and we can drag and drop our variable LT auto from the list directly into variable field. Next, we drag and drop variable PB auto into a field variable key. This variable will be activated in the PLC when we push our button. Next, we type a text that will show up in the push button and select an icon. Here we can also select how our button operates, and we set it to work direct and keep state permanent when we push it. After we hit apply, we can see our new push button. The default text size in our button seems to be too small, so we change it using bigger font. Now we'll create push button for MDI mode, and to keep the same settings, the easiest way is to simply copy it and then edit only variables, text, and icons. Next, we'll do the same for button to select manual mode and button for resetting control and indicating active error. Next, we need to save our panel. And in order for this panel to be activated in automatic mode, we must save it under name VAM automatic XML and overwrite existing file. Now we'll exit configuration and test it. First, I rearranged our windows so we can simultaneously see our HMI and our logic. Next, I'll create an error by calling a program with wrong NC command. And right away, we can see error message in HMI, active channel 1 error signal in PLC, and blinking light in our error reset button. We can click on Diagnostic button and see more information about this error. Next, we push our Reset button, see our contact PB reset go high, and error was reset. So we can see that our logic and HMI works properly. Please note that all changes to HMI were done directly in operation screen, and it is an editor independent of our engineering software. So in order to keep changes we made together with our project, we need to load changes from operating station after every modification. Now we'll go back to our PLC and work on logic to select and activate different modes of operation. We know from help file that mode of operation is controlled by combination of 4 signals. And there is a ready function block that help us setting those signals. So we go to Library Manager, then MT base additional, then POUs, channel, and operation mode. And here we can see function block MT CH op mode. We can also see here graphical view of this block and detailed description. Back to our logic. First, we'll insert new network, then insert empty box, and assign to it our function block MT underscore channel op mode. This function block must be declared, so we'll name it channel 1 op mode, and system will automatically put it for us into declaration list. We'll set input enable to be always on by simply deleting input contact. Next, we set 3 basic operation modes: automatic, MDI, and manual, using push-button contacts already declared in GVL HMI variable list. So first we place contact PB auto from our list, then PB manual, and then PB MDI. Next, we'll assign entire channel input structure as a general input to function block and entire channel output structure as an output from function block. Next, we'll add 3 additional lights: LT auto, LT manual, and LT MDI as additional outputs from our function block. And then we remove all unused inputs and outputs. So now part of the logic responsible for operation modes is ready, and we can compile and download. After download, we can see our logic running and mode of operation initially set to automatic. To test our new logic, we'll modify Windows layout and start IndraWorks operation software. Now we can simultaneously see our logic and HMI. So we can see mode automatic active in PLC and showing it in HMI. After we click on button MDI, we can see new active variable in a logic and new HMI screens. So there is a field where we can put our MDI command, and system automatically opens for us virtual keyboard so we can type it. Back to our push button panel, and we click on manual button. We can see both in PLC and HMI system switching to manual mode. But there's a problem with our push button panel in this mode, and it is still in initial configuration. So let's open panel editor. We can see here two dedicated panels. First panel, VAM automatic.xml, is activated in automatic and MDI mode. Second panel, VAM manual.xml, is activated in manual mode. So we can have different panels for those modes. But for now, we make them the same. So we open our VAM automatic.xml file and save it as VAM manual.xml. Now we can save it and verify the system is properly switching modes. In our next step, we'll work on channel feedrate override. So we go back to our project, and we can check in help file which PLC signals are controlling channel override. We can see here that bytes 6 and 7 are setting the value of override, and internally they can be called by word Q channel underscore override. Additionally, when we look into detailed description, we can see that override value will be interpreted with resolution of 0.01%. So back in our logic, we add new network, then new box, and we assign to this box a multiplier function. Next, we set an output, and we assign to it first structured channel interface 0 and out, and then our signal Q channel underscore override. Next, we'll create new variable for our HMI, and we name it FOVRD. This variable is type word and must be placed in global variable list GVL underscore HMI. Next, in the logic, we need to set our multiplier to 100 and then compile and download. After download, we'll test it using operation screen. First, we'll add a feedrate override slider to our push button panel. So controlling key will be our FOVRD variable. LED or value display will also be controlled by FOVRD variable. Text in the slider button will be %, and icon there will be following. Next, we set it as slider. That will take 3 horizontal keys, and the operating value range will be from 0 to 120. We apply our new configuration and see our new slider. Next, we exit configuration and we can test it right away. We can see channel override value changing when we move our slider. We can also rearrange our windows and see simultaneously slider in HMI and variable in the PLC. This slider will work the same in manual mode, so we need to save our configuration also as vam_manual.xml file. So when we switch to manual mode, our slider works also properly. Back in our project, and now we will work on logic to start program in the channel and to hold it. First, let's check help file and available signals. So from PLC to NC, we have signals Q channel underscore NC start and Q channel underscore feed hold. We can find more information about these signals in signal description for NC start and for feed hold. On the way from NC to PLC, we'll use signal I channel feed hold active. In the logic, first we add 4 new networks. Then in first of them, we will insert coil and assign to it our Q channel underscore NC start signal. Then we insert new contact and name it PB start NC. And with auto-declare, please make sure that this variable is declared as global and placed in global variable list GVL underscore HMI. In second line, we'll create a light for our NC start button and name it LT start NC. This variable also must be declared as global in GVL HMI. This light will be controlled by signals already coming from our NC state function block. And those will be signals channel 1 ready and channel 1 prog running. So we insert new contact and assign to it signal channel 1 ready. Then add blinker to alert operator. And then parallel to them, insert contact channel 1 prog running. In the next 2 lines, I added a logic for feed hold function. So here I created a global variable for feed hold button and name it PB feed hold. This contact controls a channel interface signal to NC, Q channel feed hold. In the last line, I create a global variable for light in the HMI and name it LT feed hold. And this light is controlled by channel interface signal from NC, I channel feed hold active. Now we can compile and download and then test it using IndraWorks operation software. We can see program running and we can start HMI. First, we add new buttons to our operation panel. This button will be for NC start. So LED variable will be LT start NC. Key variable will be PB start NC. Text will be start. And the icon will be like this. Second button will use variables PB feed hold, LT feed hold, text feed hold, and this icon. Now let's save this configuration and test it. First, we'll move our windows so we can simultaneously see PLC and HMI. Next, we'll switch to MDI mode and then type one simple NC command, for example, G1, X200, Y300, Z100 with feed rate F3000. Then, after we hit enter, we can see channel ready signal in the PLC and ready icon in HMI. Next, we set feed rate override value to 100% and hit start. We can see right away all axes running. HMI icon is showing status running, and PLC signal channel 1 underscore prog running is on. Next, we hit push button feed hold, and we see all axes stopped. Signal channel 1 underscore prog running is still on, but signal from NC I channel feed hold active is also on. And on operation screen, we can see icon feed hold active, channel status icon is showing stop, an additional icon shows system waiting mode. To go out of feed hold mode and continue our program, we hit start again. We can also verify here our override function and see our axis slowing down and speeding up. This test concludes our presentation. Thank you for your attention.